We are going to look now at the modeling problem called algebraic loops. When you assign the causal marks to a system and the causal marks don't complete, something is funny with the system. Something is not quite normal. So I think we need to examine that situation, and for that purpose I have an example that I want to show you. So we're gonna take a look at this example right here, which is a very simple one, but well, let me close from here. But if you put this into the ChemG software, the causality is not going to complete. So in fact, I would like to see if we experiment that and maybe put the system to the side over here and right here, and then we go and try to build it in the ChemG software. So let's do that, and I illustrate this problem because it doesn't seem very difficult. This problem, you have 3 loops, you have the 3 1 junctions in there. This is the voltage here, you have the R element here, this has the R element here, this has the R and the C on this side, and then all of a sudden we have this dotted lines indicating that the causality does not complete. Now how did that happen? We are going to go over here to the software itself, and we are going to look at this and build the system right here. So you have the SC over here with a 1, and then you have an R element right there. So we go ahead and do this, and then we have a 0L, which is go from here to here, and then we have an I element in here. There is the I element. We go from here to here, and then you have a 1, which is like this, and then you have the R element right there from here to here. Then we have the 0, which is like this, and then we have the I, which is like this, and then you have the 1, which is like this, and the R element. You see in there, right there, you see these are, the causality doesn't complete in there. There's a whole causal path that is red, and if I put the last element, it doesn't do anything to fix it. Do you see what I mean? See? So if you have a situation where this happens, we need to understand what we're doing to fix it. So this presentation has the objective of showing you in a very organized way what we're going to do. Just give you a little introduction. I want you to understand the nature of algebraic loops. I basically started it. We started with the fact that our bond graph has revealed us that the causality is not complete, and so we need to understand what the constitutive relations and equations of algebraic loops are, because that's where the crux of the matter is. That's where it shows up, is on the equations. Then we need to look at the ChemG generation of system of equations with algebraic loops, and then at the ChemG solution of algebraic loops. What do we need to do? First of all, to automatically detect algebraic loops, which I have shown you just a moment ago. Now we would like to have explicit state space form for systems that have algebraic loops, because when you have an algebraic loop, basically you have an implicit set of equations. What does that mean? It means that one of the unknowns on the system requires an additional equation that simultaneously with the original system would be able to solve. And then you have, what is the physical meaning of the ChemG solution for algebraic loops? I have a model of a valve spring in an engine to show you that. So let's go take a look in here. Now you see, how can we do this? We could arbitrarily go and assign the causal marks to one of the elements, right? And what I would like to do is, just as we are arguing this, I would like to do that to the system that we have in here. So you see, here is the R element, and in here is the bond graph model. And what we would like to do is assign the causality to this. But the moment you assign, you already know that there is some difficulty here. The moment you assign the causal marks, you have already identified this problem. So what I'm going to do is, I'm going to go here and say delete this assignment. I don't want this element. I'll erase it completely, and I am going to put a see, this RE means resistive element where the specification for the effort is made. There we go, like this. See, and is yellow in color here. Okay, and you see I have fixed part of it and did not fix the other. See, we assigned this, and then obviously something didn't quite work right. Sorry, I did. This is the problem. I think I reversed the order. Do you see what I'm doing is I'm doing this one. See, that's what is behind. See right there. I thought it's not this one. So please excuse me about that. Let's do this. We're gonna do the other two. So don't worry. We will get to it, but first we're dealing with this one, because that's when, see, that's where this causal marks did not complete. So you will have to assign another one in here, right there, for it to complete. So what I'm going to do is I'm going to do the same thing. I'm going to say delete this, please, and replace it with an element that I know I can work with. This is the element R that has the flow assigned right there, and that also becomes a yellow. See, that yellow has this too. These two yellows that you see in there have actually helped us complete the causal marks, and ChemG will not produce this differential equations in the same way as we do it for the other, but they will produce the differential equations with the algebraic loops. Later on, we're going to see what the proposed solution is for CAMG to do that for you. But right now, here we have finally completed. You may be wondering what will happen if you click on the interface. This is not going to work because we have this implicit form. But what you can do here is, in here you have this files that says list, records, and equation files. These three files produce the equations with the algebraic loops, the implicit equations. So you could actually do that if you, I think if we go over here, you see it's gonna try, but it's not gonna work because we cannot, see, it's not, we can't do that. However, if you look at the in the temp files, on the working files for CAMG, which is this working file in there, if you have all these equations that has this record file, we're gonna open this. There's the list file and there's the records file. So if you do this, edit with Notepad, see the computer here. See, this would be the equations, but these individual equations have an implicit set of equations. So that's the problem. And so let's go on and see what the answer is. Here are the set of equations, and what we need to do is to show you that this F2 that was assigned would need to have an extra equation to solve. CAMG will, see right there is the one, will generate these equations that are implicit set with one algebraic loop. So you see, you will have from the bond graph, you have three differential equations in here. Actually, you need a fourth one, this F2, because it's in all of them, that is as a function of the others. So implicit set of equation implies that you have the same derivative on both sides of the equations here. So what to do with this? Okay, so this one has the two algebraic loops, right? So these are the three differential equations of the system. But you see, if you try to get E2, you will always go in a loop. That's why it's called algebraic loop. So E sub 2, as a function of the state variables and the inputs, you try it here and you try it there. So you have the so E2 is some voltage there, and F sub 6 is going to be a current in there. So if you have two algebraic loops, in this case, you're gonna need these two equations. Okay. Actually, in this case, we need E11, we need F3, and we need E6. What the ChemG solution to algebraic loops? This is what we have on the board. We had a moment ago on the board. You saw how derivative form was causing these problems. And if you replace 1, then you still had 1. We saw that too. If you replace both of them, these two, it means there are two algebraic loops, and the equations will have f variables that need to be changed. So in here, you see, in here you put in this, and if you export it to MATLAB, like I said, there will be an implicit set of equations, but you have assisted to complete the bond graph model for the system at hand. However, let me explore a little bit more in detail the physical meaning of algebraic loops, because you see here this is a spring of a cylinder valve of an engine, and so they are in each winding of the spring of the valve, you have this C and the R element. So you have 1, 2, 3, 4, 5, 6, 7, 8 algebraic loops that need to be resolved for this case. So you begin to see where it becomes useful. So I found out that you can actually build these matrices, which I call it auxiliary matrices, on the system here in such a way that you can convert from one implicit system to an explicit system. dP4 dt is SE1 minus E2. BPO dPO is equal F6 times R10, and you have dQ11 F6 times P8. So you see, even if you replace it, you still come back to the same over and over. The comment I'm making here says now we must find E sub 2 and F sub 6 as functions of the states and the input. So if you do that, things if you do that, then we'll be able to set up the system in matrix form just like you see on the board. So what I'm saying is that when you have a derivative form on the equations, you have the matrix A, matrix B, but you have something else in here, this J. Okay. In order to do this, we need to symbolically generate the states matrices and say, look, with the algebraic loop, we have an additional term, and that additional term in turn needs to be put in. See, we need to find this value of A. Okay, so going back to what I was saying is you have the system with the derivative form, you have the state space form, the first one, okay, and then once you do this, you identify those matrices and the extra matrices, the extra equation that we need to have. Then we plug it in into the main equations, and what will happen is once the loops are resolved, the system A and B matrices can be calculated very easily. So in order to solve the loop, I am going through this matrix multiplications that you see in here. And then we have it in here, the A and B matrices. So for the outputs also you need the same thing. Cx plus D originally means plus the output times A, and A is this. Okay. And here you have the definition for the outputs for the C and the D matrix as well. The C and the D matrix needs to be formed with the in terms of the state variables and the inputs. And in doing that, for that example, you see is produce a change in the matrix, in the A matrix, the B and the C and the D. Okay. Once you have identified and put the matrices, then you can do transfer functions that would allow you to do the step input and the transient response, which is an impulsive action, or you can have this kind of response, this one or this one. So it's called time and frequency domain simulations. Conclusion. We want to understand what algebraic loops are, what the constitutive equations of algebraic loops are, and we have seen also how that generation of those loops affect your system. And then you have physical meaning of the CAMG solution. If you have it in here, if you have it in here, fixing it, you see it's like this. Let's say we take these two components away. We have created an opportunity for derivative form, and that would be in see here we have taken them out and asked the question, what is the system, how is the system going to respond? And if you do some more, you get some more, you get more derivative forms. So that's what the conclusion is. Conclusion is that we have a computer-generated solution for algebraic loops that is possible for a single algebraic loop or a multiple algebraic loop. Solution is independent of the system order, the number of loops. Okay. So it's valid for linear or nonlinear systems, and of course it opens the door for solution of a new set of state space equations. And this joins two technologies, classical block diagrams and of course bond graph modeling. And then CAMG is integrated with MATLAB. So, okay. So let's stop now. I think we have achieved what we set out to do.